So for this lesson on probability, we're going to take a look at independent and dependent events. This is a topic that we've touched upon when we looked at counting techniques as well, and the concepts behind it are the same. The idea is if you have two or more events occurring in the experiment that you're either performing or that you're considering, that means that you've got what's known as a compound event. So a compound event means you've got two or more separate events that are going to be considered together to make some kind of overall result. We've done a lot of talk about things like flipping coins. So for example, an example of a compound event, flipping a coin twice in a row. So you have one coin, you flip it once, you record the result, then you flip it again. It turns out that if you had two coins and you flip them both either consecutively or you flip them simultaneously, that would also be an example of a compound event. So when we talk about coins, when we talk about dice, when we talk about spinners, it doesn't matter whether you do one after the other, or whether you do them simultaneously. Decks of cards are a little bit more complicated because with a deck of cards, you can create a compound event. Using a single deck of cards, you can create a compound event where you draw a card, look at it, record the result, and then replace it. Or you could also draw a card and then not replace that card into the deck. And these two scenarios, or these two conditions, will change how you look at the probability of a particular compound event taking place. And this is just another one that I made up to try to illustrate this idea. If I had a street where, let's make, for the sake of simplicity, I had a T-junction, and let's say that there were four or three stores on one side of the, or one direction down the street, and two stores down the other direction. So when I get to this junction, I can turn right or left, and then I can make a decision about whether or not I'm going to go into one of these stores, that sort of thing. So I could create a compound event based on whether or not you choose store 1, 2, 3, 4, or 5. So there are all sorts of things that you can do to create a compound event, and most situations that we deal with, unless they're incredibly simple, like flipping a coin or rolling a die or drawing a single card, most events that we deal with are compound events. Now, the simplest situation to consider is usually when the events, or when the events that make up a compound event, when the individual trials are independent of each other. So when those events are independent, then we have a very simple calculation, and this calculation can be expanded or extended. So basically, if A and B are independent of each other, meaning that no matter what the result is of A, the result in B couldn't care less. It doesn't have any effect. Then the probability of getting some result A and some result B, we just multiply the individual probabilities together. When I say that you can extend this, you can extend this in this way. You could say the probability of A and B and C, because they're independent events, that would be the probability of A times the probability of B times the probability of C. As simple as that, when the events are completely independent of each other. So I mentioned coins being a very simple version of this, and that's a good example. So here we have a coin being flipped and a die being rolled. Two simple events on their own. Determine the probability of flipping tails and rolling a 4 using the product rule. So for part A, we want to know what is the probability of flipping tails and rolling a 4. So I'm going to use this shorthand to denote that. The probability of tails and 4. Now, does my flipping heads or tails have any impact on what will get rolled 1, 2, 3, 4, 5, 6? No, it does not. So that means that these are independent events. And it's because they're independent that allows me to use the product rule. And so that means that the probability of getting a tails and 4 is the same as the probability of getting tails multiplied by the probability of getting 4. The probability of getting tails for a coin is 1/2. And the probability of getting a 4 for what we call a fair die, which means the chance of getting any roll is the same. So a balanced fair die has a 1 in 6 chance of rolling the number 4. And so from there we end up with a probability of 1/12. Tree diagrams are something that we've also looked at in the past when we were looking at counting techniques, and it can be applied here. So a tree diagram, actually there's a couple of ways I want to show you that we can make use of a tree diagram here. So let's start off with, first we're going to flip a coin. So when we flip the coin, we could end up with heads or tails. Now that I've flipped the coin, I'm going to roll the die. Now rolling the die gives me many more branches here. 6 branches, 1, 2, 3, 4, 5, 6. And then if I flip tails, 3, 4, 5, and 6. So there's my tree diagram. And when we looked at this with counting techniques, we would now just say, okay, let's figure out what the desired path is. So tails is what I want, and then 4 is what I want. So in this case, from a counting perspective, we could say the probability of tails and 4 is equal to the number of ways that we can get tails and 4 divided by the total number of ways that we can run this experiment. The number of ways to get tails and 4, there's actually only one pathway that leads to this result, so that's a 1. And then the total number is there are 6 pathways here, 6 pathways here, and of course we end up with the same answer, which is 1 out of 12. There is actually another way that we could use a tree diagram to set up the same experiment, and it involves probabilities, the idea of the product rule. So what is the probability of getting heads? It's 1/2. What's the probability of getting tails? It's 1/2. Once I have flipped this, whether it's heads or tails, what's the probability of getting 4? Well, there's a 1 in 6 chance of getting 4. And you know what, for completeness, I'm just going to label this one as well. Now this one up top that I labeled doesn't actually matter because that pathway is already disqualified because we didn't want to flip heads. Only this pathway to tails, that's the first one we want to take, and then the pathway to a 4, and as you can see, so or the probability of tails and 4, well that's going to be equal to 1/2, which is the first part of my probability pathway, multiplied by 1/6, which is the second part, and of course once again for the third time we get the identical result, 1/12. These are independent events. They have nothing to do with each other. We're just grouping them together to make a compound event. Okay, how about another set of independent events? Once again, we're looking at coin flips. You might try this one on your own. What is the probability of getting 2 heads in a row? The probability of getting 2 heads is equal to the probability of getting heads times the probability of getting heads, because you know what, let me write this a slightly different way. Instead of writing it as 2 heads, because that might look like this, how about we say the probability of getting heads and heads, meaning there's actually 2 of them in total, 2 flips in total. Well, we know that the probability of flipping heads is 1/2, and if we run this independent trial 2 times, I end up with a probability of 1/4. I could have illustrated this with a tree diagram, heads, tails, heads, tails, heads, tails. And then we look, well, to get heads and heads, I have to go there first and I have to go there second. Those are my only options. And so there's 4 possible outcomes here, but only one of them leads to what I want. Or another way is I've got a 1/2 there and I've got a 1/2 there, and I multiply them together just as I did here, and I end up with a probability of 1/4 or 25%. What about 5 tails in a row? So the probability of, the reason why I originally was going to write 2h for 2 heads, same thing is true here for 5 tails, because I don't want to do tails and tails and tails and tails and tails and tails. So the probability of getting 5 tails is going to be the probability of getting a single tail, but there are going to be 5 of them. And so I still am going to end up writing out something that's longer than I would normally want to deal with. So there are the 5 of them. And that is going to be, each one of those is going to be a half, but there are 5 of them multiplied together. So that's actually 1/2 to the power of 5, and that is 1/32. Then we have given 4 heads in a row. So this has already occurred. What is the probability that the 5th is also heads? Now this is an interesting one, and I'm putting this in here to kind of just show you that you can slip up depending on the wording that's provided. If we have 4 heads given, that means that it has already occurred. Okay, so when it says there are 4 heads given, that's already occurred. So what that means is we've already got heads, 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 heads. And now the question is, what will the 5th result be? And as you can see from this, these have already happened. So that's done. There's no probability associated with that because of the wording of the question. Imagine it's like we've got four coins already. So out of our 5 coins, 4 of them have already been flipped and they're sitting on the table and we're looking at them. This question is saying, given that you have 4 coins that are already turned up heads, what is the probability that you will get? Actually, let's put a question mark there. What is the probability that you will get heads on this 5th toss? And of course, we know the answer to that. Assuming it's a fair coin, the probability of heads on the 5th toss is just equal to 1/2. Okay, now let's take a look at the other general type of event that we look at, which is called a dependent event. So in a dependent event, the occurrence of the previous event influences the probability of the next event, and it's called a conditional probability. Before I start talking about the algebra of it, I just want to go back because now I think we're ready to talk about these examples that I gave. Flipping a coin twice or flipping 2 coins. I've done a couple of examples that involve coins. I think you can see that these are independent. Drawing multiple cards from a deck. Oh, this says desk. That's supposed to say deck. With replacement or no replacement. If I draw a card and then replace the card, and normally when you see replacement, I think I'll put a note here. A replacement implies a shuffle. Okay, so it implies that you're going to put the card back in and then you're going to reshuffle the entire deck. So if you have replacement, then that is an independent. If you have no replacement, standard deck has 52 cards, but when you take out a card, that goes down to 51. And then you take out a card and that goes down to 50. So that's an example of a dependent event. or yes, a depounded compound event, because once you take out one card, that card is no longer available to you, and the number of cards that are still available has changed. So the probability is going to constantly be changing. And then this example I made up, turning left or right at an intersection and then entering a store. You can only enter stores 1 and 2 if you turned left. You can only enter stores 3, 4, and 5 if you turned right. And so in this case, we also have a dependent event or a dependent situation. Okay, so let's go ahead and now let's take a look at what the algebra of a dependent event looks like. It's kind of an odd looking terminology the first time you see it. So if you have these two events, the probability of getting outcome A and outcome B, it's based on, well, the first thing that you do is you check for outcome A. So the probability of outcome A is where you start. But then, because these events have some dependency, we're not interested in the raw probability of B. We are interested in the probability of B given that A has already occurred. And I really think that my example of the street where you turn right or you turn left, and then you're choosing between 1, 2, 3, 4, and 5, the probability of entering store 4 has something to do with whether or not you turned right. And so first of all, you have to figure out, well, what's the chance I'm going to turn right? And then once I've turned right, then I can talk about the probability of entering this store. So this is the overall equation that we're going to make use of. The probability of A and B is the probability of A times the probability of B given A. Sometimes usually this is more of an algebraic exercise. You might be given both of these parts. You might be given this part and this part. Technically, you can be given any two out of the three. So just don't forget that you can algebraically rearrange it if you need to, if that's convenient. But of course, in order to be able to do that successfully, you need to be able to recognize what each of those parts looks like if it's given to you as data. So let's conclude by doing an example that makes use of a dependent event. 2 red checkers and 2 black checkers are placed in a bag. We're assuming it's an opaque bag, meaning you can't see it. When you reach inside and you feel around, you can't tell the difference between a black and a red checker. What is the probability of drawing black then red, assuming the checkers are not replaced? And again, if this was replacement, it would change it into an independent event. But this is dependent because we are not replacing the checkers. And it says to include a tree diagram. So I think for the sake of explanation, it's actually easier to start with a tree diagram. When I reach into that bag, I can't see what I'm pulling out. What could happen? I could pull out a black checker. I could pull out a black checker. I could pull out a red checker. I could pull out a red checker. That's my first draw. There are 4 checkers in the bag. I could pull any one of them out. And I could pull any one of them out with equal probability, which means each of these has a probability of 1/4 or 25%. Now, let's say I drew a black checker. Well, what are my options now when I reach into the bag for the second time? There's 1 more black checker in there, and there are 2 red checkers in there. If I labeled this, we don't do this, but we can think about it this way. If I labeled this black checker number 1 and then black checker number 2, well, that would mean that there's 1 black checker or both of the reds. If I pulled a red first, there are 2 blacks left and a red, or I could pull 2 blacks and a red. And now from here, let's look, we want black then red. So what is the probability of drawing black then red? So if we take a look, well, how can I draw black first? There's one way, there's another way. Once I've drawn black, how can I draw red? 1, 2, 3, 4. So from a counting perspective, the probability of getting black and red in that order is equal to 4 total results out of 12 possible results. And 4 divided by 12 is the same as 1/3. Another way I could do this is I could say the probability of a black and a red is equal to the probability of black. So basically, that is the one that happens first. And then I multiply that by the probability of getting a red given that a black has already occurred. Now, what are those going to look like as far as numbers go? What's the probability of getting black? Well, since there are 2 blacks and 2 reds, there's actually a 1/2 is the chance of getting a black. And then what's the probability of getting a red if I already have a black? That's what this part's saying. Red given black means what is the probability of getting red if I already have a black? Well, the probability of getting red if I already have a black, let's just focus on this single black. If I've got this one black, what's the probability of getting red? It's now 2 out of 3 results, or 2/3. And if we take a look at that, we could do this 2 ways. One way is just to say, okay, 1 times 2 is 2, and 2 times 3 is 6, and then we reduce that. Or we recognize right away that we've got a 2 in the numerator, divides out with a 2 in the denominator, and those both just become 1s. And so I end up with 1/3, or I could go straight to that answer from there. And I think the last thing I want to end with here is I want to show you another way that we could have drawn this tree diagram. I could have drawn this with only 2 branches. I could have said I can get a black or a red. And the chance of getting a black is 1/2, and the chance of getting a red is 1/2. And then from there, if I've got a black, I could get a black or a red. I could get a black or a red. If I already have a black, there are 3 chips remaining, or 3 checkers remaining. I have a 1/3 chance of getting black. I have a 2/3 chance of getting red. If I already have a red, I have a 2/3 chance of getting black, and I have a 1/3 chance of getting red. So you can merge some of these branches so long as you've thought it through and you're sure that in merging you haven't lost any information. Now this type of tree is a probability tree. It's not a counting tree. So this type of tree is for counting. It tells you the total number of possible outcomes, and then you can look at the outcomes that satisfy the event you're trying to create. Whereas this tree requires a bit more of an understanding of the probabilities involved, and it allows you to use the product rule to calculate the probabilities as you go down these pathways. Because as you can see, the probability of black and red, we've got the probability of black along there, and now that I already have a black, I can follow down that probability branch, and we end up with the same calculation, 1/2 times 2/3. It's a subtle difference. It looks like I'm just multiplying like I did in the previous case with the product rule, but you need to understand that this 2/3, that 2/3 right there, that is the probability of getting a red given that a black has already occurred. This one, for example, is the probability of getting a black given that a black has already occurred, because it's based off of that. Okay, I think that's enough of me talking about this. There is your suggested work from our textbook.